Okay, so now we will talk about how to actually solve a linear program. There are two dominant classes of algorithms. One is, so both are variations. No, there are two dominant classes of algorithms. One is the simplex algorithm, the other are interior point methods, and then there are many variations of either. And there is a little bit of history here. This is from a book called Algorithms by Dasgupta, Papadimitriou, and Vazirani. And I think there is a open source. I think there's a PDF of it on the web. And they write the story very nicely. So there was the simplex algorithm, which usually works quite well, but you can construct mean examples on which it will do arbitrarily bad. So on mean examples, the simplex algorithm will require an exponential number of iterations. And hence, for a long time, as they write, linear programming was considered a paradox, a problem that could be solved in practice, though not in theory. And then in the late 70s, a Soviet mathematician invented the ellipsoid algorithm, which had provably polynomial runtime. And as you can read, the community in the West was shocked. It was a mathematical Sputnik event. People were suddenly worried that perhaps the Soviet Union was superior in this important area of optimization. And this was indeed an area which was highly relevant to the Cold War as a whole. And to understand this, it is important to know that looking back at, for example, both the First and Second World War, these were essentially wars of attrition, and there was much research into how to optimally interdict, in quotation marks, the transport networks of the enemy. Yeah, so a big body of operations research was conducted in that setting. And for example, this max flow min cut problem arose from the task of trying to find out which railway lines of the enemy, for example, you should bomb in order to cause, maximum havoc or problems in bringing supplies to the troops with the minimum quote-unquote effort. Yeah? And so both sides understood the importance of this research into how to optimally solve hard optimization problems. So this is why people were not just, it was not just a matter of honor. It was, from this military viewpoint, it was a serious reason for concern. Yeah? If the other party looked substantially superior, which in this case it did, because one side had a polynomial time algorithm, the other did not. Yeah? So people were worried. And however, this algorithm was nice in theory, this ellipsoid algorithm, but not quite as good in practice. And then a few years later, Narendra Karmarkar came up with an algorithm that was, in addition, also practical. It was the first algorithm of the class that's now called interior point methods. And this is the algorithm class that we're looking at today. And just by the way, this Papadimitriou is the same Papadimitriou who is also an author on this book, Logic Comics, which I can recommend if you're interested in. It sheds a light on a particular branch of philosophy, and it gives a light-hearted account. It's a comic book. I quite like it. Okay, but now to the algorithm, which in a way, should be very popular with physicists because it has a physical, or it builds on a physical metaphor. The metaphor is that we have some feasible region some polyhedron, and we now charge all of these sides of the polyhedron, and let's say we all charge them positively, and then we have a positive point charge that we put into this box. We have an infinite potential outside, and what you see here in dashed are the equicontra lines of this potential. So our probe charge would presumably end up here. And now we can, in addition, introduce a reward vector. And this reward vector will act as a force on this probe particle. And as we make this force, the reward force, stronger and stronger, this particle will trace out a path, which will eventually, as the force goes to infinity, take me to a corner of my simplex, or of my polyhedron. Okay, and so what this barrier method does at heart is that it turns a constrained linear problem into an unconstrained nonlinear problem. So you trade one difficulty, the constraints, for the other, namely the nonlinearity. And by the way, this picture here is from a set of lecture slides by Vandenberger. He has a very nice course on optimization. Okay, so we introduce these barriers, and then we use Newton's method to find the minimum, and then we increase this attractive force by the reward, then we resolve, and so on and so on. Okay, so the Newton algorithm finds in a single step the minimum of a second order Taylor expansion around the current solution. And this minimum is found by taking the first derivative and setting it to 0. The x here is a vector, excuse me. This here is the Hessian matrix. The matrix holding all the second derivatives. So there's the second order Taylor expansion. Its derivative is set to 0. And differentiating with respect to x gives us here the grad minus product of the Hessian matrix and the point around which we expand. And So let's say we have some surface here, we have some point x0 around which we want to expand. Then we fit a parabola to this point. Oh, excuse me. I will blame it all on this digitizer. Okay, so here's my function f. Here is my second order Taylor expansion. And somewhere there is its new minimum, let's say x new. And so if indeed our function f is just a parabola, then a single step is enough to go into the optimum. If it's not a parabola, well, we will have to iterate this multiple times. Okay, so solving this equation here for x gives us the following update. The new x is the old x minus the Hessian matrix inverted multiplied with the gradient around the old solution. So this is the Newton step. Okay, and now we introduce this kind of repulsive potential from the walls of the polyhedron. And it is popular to use a logarithmic barrier. Let's say in one dimension, this is the constraint that I have, and now I want to only allow solutions in the half space to the left of this. So we can use a barrier that diverges here, and that is infinite on the, so our potential is infinite on the right hand side, and on the left has this kind of behavior. And the barrier used here is the negative logarithm, and we have one barrier per constraint. And now we sum all of these potentials coming from the different walls of the polyhedron, we sum all of them up. And so in our feasible region, this is what we're using. And outside the feasible region, we set the potential to infinity. And this is now this potential phi of x, which you see on the left-hand side. And again, this picture and the whole development here can be found in the lecture slides from Vandenberge, or there is a very nice book by Boyd and Vandenberge. It's a great book called Convex Optimization. It is up to date and very easy to read, and available, I believe, on the web as a PDF freely. Good. So this is a friendly function for a Newton step. Because we can easily take the first and second derivatives here. So the derivative of the log is 1 over its argument. So minus previously. And then the derivative of the argument itself. And this thing here is a scalar, and that is a vector. And it can be written in this form, where again the matrix A, as before, has A1 transpose, A2 transpose, and so on, up to AM transpose in its rows. And D is a collection of these scalars. Okay. And similarly, you can compute the Hessian matrix. I'm only writing down the result here. So by this notation here, I want to say that we construct a matrix which has D on its diagonal, the vector D on its diagonal, and the 0 elsewhere. And then this matrix is squared. For the diagonal matrix, this just means we squared the each element. Okay. And just by the way, in the feasible domain, this barrier is convex, and if we take a sum of convex functions, the result is also convex. But in this case, you can also show it explicitly by looking at this matrix and asking whether it is positive semi-definite or not. And you can write this as Y transpose, and then this matrix A transpose which can be rewritten as the squared Euclidean norm of some vector. And we know that a vector must have a length of 0 or more. So what we see is that this thing here is positive semi-definite because this holds. So we have a curvature that is always 0 or larger than 0, and this means that our potential function phi is convex. Because it has non-negative curvature everywhere. Okay. Now we will try and let our probe charge go to the minimum of this potential. And if we disregard the cost or the reward in the objective function for the moment, then we can compute what is called the Analytic Center. Which is characterized by having a 0 gradient. You have to note here that the different specification of the same polyhedron can give us different analytic centers. Okay, so different specifications of the same polyhedron can give different analytic centers. Because we can always add constraints that are redundant. So let's say this is our polyhedron, and I could show some equicontra lines here. And, excuse me, and if I now copy the same polyhedron, but if I try and recreate the same polyhedron here, I can now add, so I'm showing the feasible region here. I can now add extra constraints. For example, constraints that are totally non-active because it lies outside the feasible region, or that are barely active. Let's say like this. They do not change the feasible region, but they will change the barrier, or they will change the potential function. So for example, in this case here, the optimum would be located or would be pushed closer to the opposite side of the polyhedron. So for the physicists, we can interpret this phi of x as a potential. And that gives us a force, which is minus the gradient of this potential. So this would be the force, and then we could say that phi is the potential of 1 over r force field associated with each constraint plane. So when I was talking charges, this was not, not a perfect metaphor, because there we would have a 1 over r squared force, and here we have a 1 over r force, but the idea is the same. Okay, and now we want to introduce our objective function. So now we add a force pulling in the direction of the reward, or pulling against the direction of our cost. This is if we have a maximization problem. This is if we have a minimization problem. And then I want to minimize the sum of this attractive force scaled by a parameter t plus the potential. Here for some parameter t larger than 0. And because I want to find the position, I'm using the argmin here. And this gives me a new solution, x star of t. And this x star of t, a function of t, is then called the central path, which I had previously plotted in this example at the beginning. So this thing here was the central path. And on the central path, excuse me, we know that the derivative of the above expression has to be 0 for every choice of t. So we have that t times c plus the sum should be 0. And altogether we have that the path is always orthogonal to the local control lines. Okay, and we now have an algorithm where we start with some value of t, then we find the optimum, we increase t, we find the new optimum, and so on. And this is an algorithm called the barrier method. I assume that we already have some feasible starting point, and it is not trivial to find a feasible starting point in general. If we have time, I'll say more about that. And we start with some value t larger than 0, and with some tolerance and some user-defined step size mu. And then we repeat the following steps. We compute an update x star for the current value of t using Newton's method, starting at our previous point x, and this is called an inner iteration, or typically we need several Newton steps, so these are inner iterations. We update, and then we increase the pulling force by saying t equals some factor times the previous t, where mu is typically somewhere in the range of 10 to 100. And these are called the outer iterations. Which we repeat until m, which was the number of constraints, divided by t becomes smaller than our tolerance size. Okay, so very simple algorithm. And I here have a picture, again from the Vandenberger course, which shows us this trade-off for different step sizes. If mu is small, then we will have many outer iterations and few inner iterations. So that means we change the pulling force only slightly. So our Newton method will converge quickly, but we need many of these outer iterations. We need to adjust the strength of this pulling force over very many iterations. If, on the other hand, mu is large, then we have few outer, but many inner iterations. Yeah, so it's a trade-off, and it seems that the performance is luckily not terribly sensitive to it. So here you see the quality of the solution. Lower is better as a function of the total number of Newton iterations, so the total number of inner iterations. And you see that if we increase the pulling force in big steps, then we need very many inner iterations before we get to some good enough performance level. If, on the other hand, we increase this pulling force only very slowly, then I only need relatively few Newton steps each time, but I need more iterations. And you see, overall, the order of magnitude of iterations required here is the same. Yeah? So the big picture is that it does not matter very much, which is good news. Yeah? So it's not terribly sensitive to this user-defined parameter of mu. Do you have any questions so far? Yeah.
We've chosen a log function for the barrier.
Mm-hmm.
Is there a particular reason for it?
Only because the first and second derivative look so nice, and because it gives us a function that is smooth everywhere. So if we certainly don't, we would not like to have any kinks in this resulting potential function. So, what functions can we think of that somehow go to infinity and to some low values on the other side? Presumably we could have used some exponential, but the derivative of an exponential is more expensive to compute, and so this is really the main reason that it has the right property of going to infinity, and it has a simple derivative, and it does not induce any kinks anywhere. It's a nice and smooth function, so it's an arbitrary choice, but a good one.
Because I think if we start with 1 over ax, then we end up with a physical 1 over x squared potential.
Yeah, yes, you could do that, and then you would have the proper physical analogy. Yes. Other comments or questions? Okay. Good, then we still have time to tackle the last open point here, namely, I was assuming that we already have a feasible starting point. And if you work in millions of dimensions and so on, these are by no means easy to find. So here's a clever solution. I like to think of it as a Münchhausen solution. Yeah, so we have an algorithm that needs a feasible starting point, and we use this very algorithm to find a feasible starting point, but we set up the problem in a different way, namely such that it is, for this auxiliary problem, it's trivial to find a feasible starting point. And we use this auxiliary algorithm to find a feasible point in the first place, from which we then start the actual computation. So, Münchhausen style, we introduce an auxiliary variable w, and we now minimize over w and x, and w is a scalar, and we want to minimize this scalar such that the following holds. These are almost the constraints we've seen, except that w is added to the right-hand side, w multiplied with a vector of 1s. And we also require that w should be no less than 0. And for this auxiliary problem, it is easy to find a feasible starting point, so a point which does not violate the constraints. Namely, we can set x to 0, and then we have to choose w large enough so that b plus w times this vector of 1s is no less than 0. So essentially we look for if b should have all positive entries or all non-negative entries that we're already done, and if b has a negative entry, then we need to make w so large as to compensate for it. Okay. This can be done by saying we pick the smallest value of b and we negate it, and then we actually only want to do anything at all if this value is so we only want to do something if b is at all, if it has negative entries at all. Okay. And then this problem can be solved using the barrier method to optimize this problem. and if the optimum value of W that is now found using the barrier method is 0, then the x that we found at the same time, then x star or x optimum is feasible in the original problem. And now we have a valid starting point to now use the barrier method on the actual optimization problem that we're interested in. And like I said before, this barrier method has a guaranteed polynomial runtime. Now, how efficient it is depends on the shape of your polytope. For example, if I have a feasible region that becomes very, very, very thin, and I insist that my reward, if I say that my reward grows in this direction here, then I need to pull my point all the way into this corner against an increasing force. So this is a less nice case for the barrier method than if I have a less steep angle between the walls. But even so, this method works very well in practice. Okay, so summarizing, what we did in this last hour was we discussed a method to solve the linear program. The linear program which we need to solve iteratively to solve the integer linear program, to solve the maximum a posteriori problem in the probabilistic graphical model that we have set up. This is a general strategy which always works in principle, which in practice can become too slow if you look at sizable problems. And in the exercise today, you will actually use this ILP solver. You will evoke an ILP solver to address a small graphical model. You will also see that if you make the graphic model too large, it no longer works, which is why we keep talking about this topic in the next few weeks, to look at graphical models with special structure that still afford optimal solutions in polynomial time, and also graphical models which do not have this nice property, but for which we can use approximations. Thank you, and then see you next Tuesday.